Hello, everybody. Good morning, good afternoon, good evening, wherever you are in the world. Welcome to this CCM webinar on transfer standards. My name is Andy Knott. I'm the chair of the CCM's working group on Force and Torque, and will be chairing this webinar today. We have two presentations for you, and it's my pleasure to introduce the presenter of the first presentation, which will be on the impact of transfer standards and their uncertainties in the field of fluid flow. Before I do that, I will just say, please could you ensure that throughout the webinar, you have your audio and cameras off, other than the presenters. If you have questions to ask that come to mind during the presentation, please use the chat box to ask those questions. There will be a discussion after each of the two presentations, and there is a raise hand option on the Zoom bar, so you can use those to raise your hand, and then we can have a discussion after each of the two presentations. As the screen says at the moment, this webinar is being recorded, and the presentations will be available on the BIPM YouTube channel after, without the discussions. At the moment, we have, it looks like 86 participants online. We have a lot more registrations than that, so I guess people will still be joining at the moment, but we have a limited amount of time of 1.5 hours for this webinar. So the first presentation will now be given by Dr. Enrico Frahm from PTB in Germany. Enrico studied environmental engineering at the University of Rostock in Germany, and then carried out a PhD in water management and hydrology at the same university, and has been working at PTB in the Department of Fluid Flow since 2013. He's the head of the working group on the realization of liquid flow measurements in the Department of Liquid Flow there, and is responsible for the German standard of fluid flow, and his work focuses on the organization and evaluation of comparisons in that field. He also works in the field of uncertainty of flow calibration facilities, and is a member of various committees in the field of flow, including Euromet, DIN, that's the German Standards Organization, and the CCM's working group on fluid flow. So Enrico, please can I ask you to make your presentation on the impact of transfer standards and their uncertainties in the field of fluid flow. Thank you.
Oh, thank you very much, Andy, for the introduction. I will start to share my screen. Share, hopefully it works. Yeah, it's okay. Okay. Okay, hello to everyone around the world. Fantastic. It's a great honor for me to have a talk here and to give you some ideas about the impact of transfer standards and the uncertainties in the field of fluid flow. And well, the background of my topic is the complexity of comparisons, and especially in the field of fluid flow, the relationship between concerning low lab uncertainties and providing an appropriate transfer standard is always a major challenge. So during my presentation, I will try to give you an idea about this topic. Okay, this works. In the first part, I will give you an overview on the topic on fluid flow, generally about the flow value itself and its realization, and what is important to consider if a calibration facility is taking part in a comparison, and what are the special aspects on evaluation procedure. So, and especially for the use of transfer standards in the field of fluid flow. And finally, I will show you some examples on uncertainty calculation and input parameter of the used transfer standards. So first of all, just let me give you a short introduction to the field of fluid flow. So to the question, what is fluid flow and how it is possible to realize this unit? So basically, the unit flow is a derived value and an indirect value. So for its realization of the unit, it is necessary to measure other parameters like mass, time, volume, density, pressure, something like this. And each of these values is followed by its own uncertainties. And here in this schematic diagram, it illustrates the interaction between all of these input parameters when the flow, mass flow, volume flow is coming into a pipeline, passing the meter under test, and going into the reference measurement. And this is most of the time volume mass in combination with density and time measurement. So, and this basic principle applied to a flow calibration facility. There's a flow generation section required, like a pump or constant hand tank. And the fluid passes through the meter and the test into the references. And these are some examples of typical used reference in a fluid facility. Could be a scale, a volume tank, or a master meter. And finally, the water is flowing back in the circle into the pump via a storage tank. And the calibration gives a result as the deviation between the meter under test and the reference. And the transfer standard itself is has to be installed at the same place than the meter under test. So who is the typical operator of a facility? So it's a flow meter manufacturer, flow calibration providers, authorities, or National Metrology Institutes. So fluids typically used are water, hydrocarbon, 𝐒𝐩𝐞𝐚𝐤𝐤𝐬 fluids, and the flow range is from microflow up to 12,000 cubic meters per hour, with a pipe diameter of 1 millimeter up to 600 millimeters. So this demonstrates the wide range of facility characteristics, and here only facilities included which are listed at BIPM database. So other users of flow calibration facilities like manufacturers could extend of this values here. But for all facilities is required to take part in a comparison or in proficiency testings. So the aim is of this to verify their laboratory uncertainty specifications and the calibration measurement capabilities, also called CMC values. So the need of such a comparison is regulated in several standards and guidelines. Some examples are given here, like at BIPM or from EuroMet Guide or the 70025 standard. So I don't want to go into detail to that, but for all comparisons, this is essential to use a correct and valid evaluation procedure. And this brings me to the next topic of my talk, the evaluation procedure with a special focus, of course, to the field of fluid flow. So the basic evaluation procedure is based on 𝐒𝐸𝐞𝐸. So this procedure is well known and often used for the comparisons. Here, the uncertainty weighted reference value is used for the estimation of the degree of equivalence between the participants. So this so-called EN criteria is calculated by using the normalized difference between the reported value of the facilities and its uncertainties and the reference value and same of the uncertainties there. But the problem is that the method of 𝐒𝐸𝐞𝐸 does not describe a specification of input parameter to the value itself and its uncertainties. And due to this lack of specification, the BIPM Working Group for Fluid Flow, WGFF, made the following recommendations in the field of fluid flow. So as the first step, input parameter to the uncertainties of the reported lab value were defined as a lab uncertainty, the short-term repeatability of the calibrations, and all other components which can be attributed to the transfer standard. And this altogether are the input parameters to the uncertainty of the reported value. And as a second step, this uncertainty and the uncertainty inputs should be discussed for inconclusive or for detection of inconclusive or conclusive calibration results. So the central question is to find out the impact and the suitability of the transfer standard to comparisons results. But why is it so important to have a special look and focus on that? So the point is that large uncertainties of transfer standards and repeatability could lead to a decreasing of the final EN value and inconclusive results. And this would lead to a misinterpretation of comparison results, where laboratories would pass successfully a comparison despite of large uncertainties of the used transfer standard and or despite of large repeatability during comparisons. So to avoid such a misinterpretation possibility of comparisons, additional evaluation criteria for conclusiveness were introduced and recommended. So a fundamental approach of this method is that the quality of comparisons depends directly on the amount of uncertainty of the transfer standards and the need of conclusive results. So this leads to one of the simple evaluation criteria behind this discussion. So the maximum uncertainty of this transfer standard should not exceed twice the uncertainty of the lab uncertainty. So this is a very simple formula and really important, and the background, simple background of the discussion. So just let me give you an example for this. For the just recently started key comparison for large flow, the lowest lab uncertainty is 0.01% standard uncertainty. So the maximum allowed uncertainty to get results, proper results for this certification is of the transfer standard, it's only 0.02%. And it's really hard to get such a very well sophisticated meter under test transfer standard in the field of fluid flow. So on the following slides, I will give you some examples about typical transfer standards in the field of fluid flow and to the input uncertainties to the transfer standards, and how the discussed requirements can be met. So back to one of my first slides, the transfer standard will be installed, as already mentioned, at the same place where the meter under test is installed. A characteristic setup consists of the meter itself. This is the transfer meter. And an advanced setup could also include an inflow section, outlet section, and a flow straightener. And also it is possible to measure special conditions of the calibration, like pressure, line pressure at the inflow, line pressure at the outlet, and temperature. So this is a basic drawing of 𝐒𝐸 setup, which we just used in a comparison for large flow. So typical flow meters used for comparisons are Coriolis flow meters, magnetic inductive meters, and turbine meters. And each of these instruments is characterized by its own advantages and disadvantages. So if you want to get more information about use, transfer standards, evaluation procedure, and flow ranges and fluids and so on, you can have a look into the very well BIPM key comparison database. There you will find any information about key comparison, supplementary comparisons, and use transfer standard and so on. So really interesting to have a look to this database. So as already mentioned, the uncertainty of the used transfer standard is must be very low. But what are the input parameter to this meter uncertainty? This is the uncertainty of the transfer standard. In the field of fluid flow, the WGFF working group recommended to consider at least the long-term stability of the meter, it's called the meter drift, and sensitivities of temperature of the meter, sensitivities to pressure and temperature. And other additional input parameters could also be discussed and depends on the type of meter. Like sometimes a meter is more sensitivity to disturbed inflow conditions or to flow instabilities and fluid viscosities. Other example for Coriolis flow meter, it's very sensitive or could be larger sensitive to zero flow stability of the meter itself. So a detailed estimation of all of these input parameters is a very important keystone for a reliable comparison. And in the last part of my presentation, I will give you some examples of uncertainty inputs to the typical transfer standards. And therefore, I will separate between a possibility to post-process reported data of the participants, and on the other side, on a simple use and discussion of the reported data if a post-processing is not possible. So the first example deals with the temperature sensitivity of a Coriolis flow meter used in a comparison. So the motivation for the research was to the observed discrepancy between the default temperature given in the technical protocol of the comparison and the real fluid temperatures during the calibrations of the participants. So the question was, is the fluid temperature a significant difference between the laboratories of Whittlesey? What does it mean to the meter characteristics? So based on this, this was the motivation of it, and therefore we made characterization measurements using this Coriolis flow meter, and we found a very strong temperature dependency of the meter under test. So temperature changings of plus minus 10 Kelvin led to plus minus 0.04% in meter error. So this is in the background of meter uncertainty, and confirmed lab uncertainties quite important to know. So this clear temperature dependency on meter error was used for a post-processing correction of the data. So which resulted in a clear reduction of meter uncertainty. So the uncertainty of the meter induced by the original temperature dependencies gives two large uncertainty values. So in this case, the meter was not suitable for use as a transfer standard within this key comparison. So that's why we corrected this temperature dependencies. And by this post-processing of the reported data, you get a clear reduction of uncertainty. So the second examples also deal with the Coriolis data, but used in a supplementary comparison. So repeated calibrations at pilot laboratory showed a large meter drift within 3 years of calibration running. So the question was if these deviations were caused by meter drift, same as before, or by zero stability. So because these uncertainties, like this meter drift caused by zero instability setting, gave too large meter uncertainty, and the meter under this condition was not suitable for the comparison. But under special assumptions, it was possible to post-process the Coriolis data by a new introduced zero missetting method. and under special assumptions. And if this method was applied, the zero effect was clearly reduced, as well as the meter uncertainty in the lower flow range. In this case, the transfer standard was suitable for CMC confirmation during the comparison. So this was the first part. If it's possible to correct, and this must be, of course, discussed between the participants, post-processing of the data. And the last example demonstrates the importance of extended discussion about conclusive or inconclusive results is important, and if a post-processing of the reported data is not possible. And therefore, one example, this is this one here. So in this case, a turbine meter was used, and here also a large amount of meter drift over the 3 years was detected, but this detection was not systematic. So the turbine meter showed a large meter drift over 3 years, which was followed by a large amount of meter uncertainty here. So nevertheless, all labs passed the EN criterion. So on one hand side, a large meter uncertainty was detected, and on the other hand side, all labs passed the standard EN criterion. What does that mean? But following the recommendations of the WGFF, the meter drift was identified as too large, especially for 2 participants. These 2 labs exceeded the boundary layer due to their very low lab uncertainties in combination with the large meter uncertainty. So low uncertainties of lab and large uncertainty of the transfer standards. So, and that's why the results of these 2 labs were identified as inconclusive. In consequence, the used meter was not suitable for a confirmation of the CMC entries of the labs. It's important to note that the labs passed the N criterion, but during the discussion of conclusiveness, it was decided that the meter was not suitable. So this is important to separate between EN criterion and discussion on conclusive or inconclusive. So this example demonstrates very clearly that not every transfer standard is suitable for labs with low uncertainties. So basically, the lower lab uncertainty to be confirmed, so better the transfer standard must be. So in this sense, very simple example. No one would use a domestic water meter to compare national flow standards. So why not? Due to the large meter uncertainty in contrast to the low lab uncertainties. So this is just basic thinking behind this point. So finally, let me summarize my presentation. The unit flow is a very complex value and quantity with a wide range of facility types. This combination always makes comparisons to a great challenge. Nevertheless, the rules of traceability and proof of measurement capabilities still apply for this field of metrology. I try to explain that the standard evaluation procedure should be extended by a serious discussion on conclusiveness of calibration results, especially for laboratories with low uncertainties. So it is strongly recommended to consider transfer standard characteristics within a comparison evaluation. So the proven quality of transfer standards is crucial for the conclusiveness of comparisons for fluid flow, and I think my colleagues will talk about this for the other fields in metrology, like talk later on. Yeah, so thank you very much. this is a list of references. If you are interested in, you can have a look on that. And finally, if you're interested about in more information about fluid calibration at PTB, feel invited to visit this web pages here and a YouTube film for a short film about our calibration. Yeah, so thank you very much.
Okay, so Mikolaj, over to you, please.
Yes, hello everyone. Thank you, Andy, for the introduction. And thank you, Enrico, for your very thorough and interesting presentation. My name is Mikolaj Wozniak. I work for RISE. It's a National Metrology Institute in Sweden. I work as an engineer responsible for Force and Torque National Laboratory here. I'm also involved in some international activities, like I am a subcommittee Force and Torque convener within TC, Technical Committee of Mass and Related Quantities within EURAMET, European Regional Metrology Organization. Yes, I've been working here since 2017. Before that, I used to work at Polish Metrology Institute in the same field for 8 years. Yes, over to you, Andrea. Maybe some few words about you.
Yes, Mikolaj, thank you. Hello, welcome. And my name is Andrea Prato, and I work at INRIM, which is the Italian National Metrology Institute. I have a PhD in metrology, and I've been working here since 2012. Now I'm responsible for force, but I'm also involved in other mechanical quantities such as hardness, acceleration due to gravity, and vibrations. So today we will present, Mikolaj and I, this presentation about the transfer standards for force, key comparisons, and also of course for torque. So Mikolaj, you can begin with your presentation, then I will come up with mine.
Yes, thank you, Andrea.
Thank you.
So I will try to share the screen now. Let's see. I hope this is the one. Yes, should be all right. So the topic of the presentation is performance of the transfer standards in key comparisons in the field of force and torque. Since the talk is being covered by both me and Andrea, we decided to divide this presentation in two parts, which I will cover the first one. I will describe a little bit about key comparisons in force and torque, present the transfer standard that we use in key comparisons, and we came up with a list of parameters that affect the results of key comparisons, and that they are mainly related to the performance and the quality of transfer standards. And the second part covered by Andrea is will give you some practical examples on how to apply a relevant procedure in order to minimize these effects, and also how to choose a proper transfer standard for our key comparisons. So in the beginning, we would like to just share with you some key points about key comparisons in general. This can be applied to any type of key comparisons, not only field of fluid flow or force or torque, but others as well. So the scope of these key comparisons is that to have a global participation. We involve National Metrology Institute from different parts of the world, and we used to compare different techniques of realization and generation of the quantities, And of course, we try to um, um, realize everything in very high precision. So the key point, as also mentioned by Enrico, is to use a very high quality transfer standards to ensure that the results are reliable and the accurate data is being analyzed. So the primary goal of all key comparisons is to maintain the equivalence between measurement standards throughout the whole world. Some of the participants may use key comparison results to improve their measurement standards or methods. So, as I presume all of you know, that the key goal is also to support our so-called comparison, calibration and measurement capabilities. We call them CMCs. So these key comparisons that we do help us validate these key comparisons. And of course, key comparisons are support international trade and support globalization by maintaining the integrity and consistency of measurements throughout the whole world. So what we do, how we perform key comparisons in force and torque. The measurement campaign that we plan is has a form of a star, you may say. So we have a pilot laboratory that usually carries most of the work, actually, performs also most of the measurements, quite a lot of measurements. So it's a big project for such a pilot laboratory. And of course, pilot laboratory usually also analyzes the measurement data and writes the report after the measurement campaign is finished. So typically we use so-called star format, where transfer standards, we use usually at least 2 transfer standards for circulation between participants. So we have a pilot. I tried to visualize such a star format in such a sequence. First, since after initial measurements at the pilot laboratory, transfer standards are being circulated between laboratories. So at the laboratory, the specific procedure is being applied the same as at the pilot laboratory. Then each participants, after they perform their measurements, they send the transfer standards back to the pilot, where the pilot laboratory performs again the procedure. In this measurement cycle, which we usually call a loop, so pilot, participant, pilot, we can determine also so-called loop value for further analysis of the data. In some cases, in a loop, we can have not just one participant, but for example 2. But of course, in order to have a better overview of the stability of the transfer standards, we try to apply a typical star format, where in a loop there is only 1 participant. So the key goal, as mentioned, is to demonstrate the equivalence between measurement standards. So in CIPM key comparisons, at global level comparisons, we determine so-called key comparison reference value, which is then being used for any subsequent comparisons, such as RMO key comparisons being conducted after CIPM key comparisons within regional metrology organizations. So in these key comparisons, the results are being linked to the key comparison reference value through linking laboratories. Requirements and recommendations about how to perform key comparisons in general are described in a guide for measurement comparisons being available on BIPM website. Yeah, and the procedure that we follow usually is being the same as in both types or all types of key comparisons. Commonly in force and torque, we measure, we perform measurements at 2 nominal levels. And in order to have a good comparable measurement data, we apply a specific procedure which can be adapted on different so-called machines that we use to realize and generate force and torque. So these are the different measurement standards. Usually they are primary types, but also secondary. And the other reason for this specific procedure is that we are using measurement instruments as transfer standards, the same as Enrico mentioned that they are using flow meters as transfer standards. In some fields, I presume there are artifacts that are being circulated, which do not, for example, have significant drift between different measurements in time. But here we have to adapt to this specific condition. So when we are talking about different realization techniques, different types of so-called force or torque standard machines, as we call them. So as you can see, there can be different types of realization generation of these quantities. So we use a specific types of machinery to generate and apply axial load to a calibrated object or measured object. For example, a pure deadweight machine that we use weights and we use a gravitational acceleration to determine the reference value of force, or with a specific amplification systems like lever amplification or hydraulic amplification systems. In the case of secondary systems, we can have a reference transducer consisting of single or multiple transducers. And typical values for these different types of machines are provided here. All these images are taken from a Euramet guide, a calibration guide available on the Euramet website. In case of torque, it is the principles are similar. Of course, they differ because it's a slightly different quantity. They both are related, but of course the realization it's different. So for the pure primary systems, we use deadweight lever machines, where we use weights as well in the gravitational field, as well as a lever system. We can use a semi-primary systems like force lever system, visible. Its principle is visible here, where you have drives as the cubes here generating the load, and force is measured. Our forces are being measured by the force transducers, and we can have a lever system with a known length to determine a reference torque. As a secondary system, we can have a reference torque transducer system where where a reference torque, as an example, is being here, and the object is being mounted below in a specific machine of a stiff frame. So when you talk about transfer standards, well, in force and torque, the principle is basically the same. We use mainly strain gauge type transducers. Strain gauge technology is well known. And then we, to measure the signal, the output signal of the transducer, we use a measuring amplifier in the middle. And to be able to apply axial load, we use specific loading fittings or loading elements to be able to mount this in our machines. Both the transducer and the amplifier have a quite linear response to mechanical or electrical load, respectively. But of course, all these elements affect measurement results. So this is how it can how it can look in torque instead. So you can see that we can use different types of torque transducers, like a shaft type transducer, left side, or a flange type transducer, and of course various types of loading elements. Measuring amplifiers can be even the same. So this is basically the same type of measurement chain from transducer to loading fittings. So the main part of our talk is to actually talk about parameters that affect the results. So we divided these, we grouped these parameters in six points. That's repeatability or reproducibility, short-term creep, drift, parasitic components, the influence of the amplifier, and ambient conditions. When we talk about repeatability or reproducibility, this is mainly the common parameter of all measuring instruments. So when we measure the same quantity in the same or similar measurement conditions, the measuring instrument gives us slowly different values. And these two parameters describe the spread of the results. In other words, measurement precision. So we can apply, well, for a pure random variable when we measure in similar conditions the same quantity, then and we want to calculate a mean value, then usually a normal distribution can be applied to such a variable. But of course, in different key comparisons, sometimes not only a standard deviation is being calculated, but it is actually the most common. And we try to have a larger amount of measurement data that can lead to smaller uncertainties of a mean value. When we talk about short-term creep, or creep, as you may say, the creep is the tendency of a solid material to undergo a slow deformation while subjected to a persistent mechanical stress. It can be visualized in such a graph here, where you have three stages. A first stage, which is a loading stage, and the green line represents the load value. The second stage is the holding of the load stage, and third stage is unloading. So the output signal of a force or torque transducer tries to follow this change of the load, but it does not follow it perfectly because of this effect of creep. So in the first stage, we may we may have an elastic deformation, but it does not follow the load perfectly in the holding stage. Here we observe a creep effect. And in unloading, where we have an elastic recovery after this, and a creep recovery, a similar effect to creep is being also seen. And the expression of short-term creep is actually quite relatively new. In the past, creep was being measured in, let's say, 20 to 30 minutes, which took time. So therefore, it has to be underlined that short-term creep is a specific type of creep. Moreover, in secondary type reference machines with reference transducers, the measured creep is a combination of all creeping elements of the machine, such as a reference transducer or machine's part, like a frame or a lever. So when we go to a drift or a long-term stability, that is actually a crucial parameter in force and torque comparisons. And it's very important to analyze this drift very carefully to be able to determine the reliable key comparison reference value, and of course a loop value for each loop. So each transducer, each transfer standard can behave very differently in different key comparisons. I took an example from a RMO type key comparisons, key comparison Euromet K1, where in these two graphs you have measurements of two different force transducers at 5 kilonewtons, and on the left side you can see that the behavior of this transfer standard is you can see more or less a linear dependency in time, whereas the other behaved quite stable. You can see that the drift between different measurements is quite low. On the other hand, you can have other behaviors like more random behavior, where it's hard to predict how the transfer standard will behave in the next loop. Or you can, throughout the whole campaign, you can see that the transducer behaved quite stable, but at the end, at some point, you may observe a very, very significant shift, which in some cases can be very hard to investigate what happened, right? And how to apply a specific correction, or how to estimate an uncertainty related to such drift. So Andrea will be talking more about practical solutions for this. Parasitic components. Well, as you may know, force and torque are, of course, vector quantities. So we want to ensure that the best possible load transfer is being applied. So here I provided some examples of force measurements where the parasitic components are mainly caused, but not perfect verticality as a first example, or alignment here. But there can be also other external forces or bending moments that can affect the results of output signals of transfer standards. And of course, these effects can be studied more in detail, and even corrections can be also applied, but we try to minimize them as far as possible. In torque, the sources of parasitic components are basically the same. So for not perfect verticality, some results can be seen as when you rotate a force transducer throughout its axis, and you do not have a perfect verticality between plates, the upper plate and the bottom plate, between which the force transducer is mounted, then more or less a sinusoidal dependency can be seen for higher angles. For alignment, you can misalign, move away from the axis the transducer, and see that the sensitivity, the far away you are from the axis, the sensitivity of the force transducer drops. So it's very important to verify that you are measuring in a good position. I mean, you have to mount the transducer so that the axis, its own axis, matches the axis of force or torque generation. Right, and also the influence of the amplifier. This has to be considered. The amplifier that we use normally is a carrier frequency amplifier. And it's, of course, a separate measuring instrument. So we try to take the best in the world that is available to minimize influence of this instrument. But of course, its performance must be considered. The typical energization parameters that may affect the results are the excitation voltage, the frequency value, and also the filter settings. These are the examples given from this type of measuring amplifier. And also, such amplifier can have some systematic deviations. Andrea will talk more about how to deal with them. And last are ambient conditions. So most of the strain gauge transducers are hermetically sealed in order to safeguard strain gauges from external conditions that can affect them, and of course affect the result. But in any case, we need to consider the influence of the temperature of the whole transducer. In torque, very common is also to take into account humidity effects, because shaft type torque transducers, which are being applied, are not hermetically sealed. It's just not possible. So both temperature and humidity effects can affect the sensitivity. This is just an example how we try to correct if the result is being performed in different temperatures or humidity values, then we have to correct the result based on the sensitivity factors. So that was just the introduction to the principles and effects that are we consider in force and torque key comparisons. And now it's time for Andrea to continue. So I would like to thank you and give word to Andrea. Just let me stop sharing. Yes.
Okay. Thank you, Mikolaj. Okay. Can you see my screen?
Yes.
Okay, nice. So thank you, Mikolaj, for your presentation. So I will continue this presentation regarding force torque transfer standards key comparisons. So the idea in this second part is to show how these effects can be minimized during the key comparisons. So first of all, we talked about repeatability and reproducibility, which are, of course, random effects that are related to the transfer standard itself. And this should be minimized because we want to verify the CMC of our primary standards at an uncertainty level depending on the generated known reference, known force or torque value. So the idea is to perform different measurements, and usually these transfer standards are rotated through a total of 720 degrees with different steps, usually steps of 60 degrees for force transducers and 120 degrees for torque transducers. In this case, so we get a total of 12 total deflections of 12 measurements for force transducers and 6 measurements for torque transducers. As mentioned, we calculate reproducibility as standard deviation of the mean. In this case, the more measurements are performed, the lower is the uncertainty related to the reproducibility. So this is why we perform so many rotations compared to the typical standards like ISO 376. So it is not that unusual to observe sinusoidal dependency of the deflections, as shown before by Mikolaj, especially due to parasitic components. And it is possible to minimize the effect by fitting these sinusoidal curves and keeping the residual of this measuring of this fitting procedure as uncertainty component. So this can be minimized in this way. Anyway, the mounting of this transfer standard is of paramount importance in order to minimize the influence, especially of these parasitic components. Regarding the short-term creep, which is another influence factor, it is important to choose a quite long period of reading. Typically, 6 minutes are selected in order to minimize the creep. We can see here an example of a scheme of key comparison procedure. So we keep on applying different force or torque steps, and we acquire data after 6 minutes from the application of the force or torque signal. So in this way, we are quite sure that the short-term creep can be minimized since the deformation becomes very small at lower time periods. The other important influence factor is the drift and the long-term stability of the transfer standard, and this shall be individually evaluated for each transfer standard in order to evaluate its behavior in time. As shown before, we usually provide in force and torque key comparisons star type scheme in which one transducer is circulated among the different participants and the pilot. And this is the best key comparison for the evaluation of the drift of the transfer standard, since just one transfer standard is circulated. As mentioned before, one loop is defined as the cycle, pilot, participant laboratory, and pilot. Another type of scheme which was just applied once during CCM.F key 23 comparison is your bring your own device principle, in which each participant provide its own transducer that, of course, is sent to the pilot and back. This is useful because in this way the effort of the pilot laboratory are easy because you do not have to wait the time for the shipment, and so you can perform more measurement in a shortened time, but gives quite a larger uncertainties due to drift, because we have less information about each transducers, because we perform less measurements for each transducers instead for using just one for the all comparisons, like during star type scheme. Anyway, this is something that has to be kept in mind. Okay, how we can keep into consideration the drift and how the reference value is performed. Usually, we attribute a loop value, which is given by the mean value of the two pilot measurements in most of the cases. In other cases, it is also possible to correct the drift for the pilot values by considering a linear behavior of the transducer between two pilot measurements in a single loop. In this way, we can, of course, bring the reference value of the pilot at the time of the participant laboratory. As a matter of fact, our measurements are not performed simultaneously, so we have to attribute a loop value at the same time of the participant laboratory, and this is done in this way. So by using this formula, so basically a linear fit is performed between the two pilot measurements, and through a linear regression, we can calculate the pilot value for each loop, and this can be compared to the deflection measured by the participant laboratory. Okay, how can we consider the uncertainty of this drift? For example, in the case of corrections, it is typical to attribute an uncertainty in this way, so a type B uncertainty, where the width of this rectangular distribution is given by this formula and is associated with the variation of the drift during 4 days. In other comparisons, a combination of different uncertainty contributions are computed. In particular, it was found that a rectangular distribution is associated with a specific loop, so based on two values. And another part of uncertainty is considered as 50% of the mean absolute drift, which correspond to half width of this second rectangular distribution. So by combining these two terms, we can associate an uncertainty due to drift. In particular, these 2 and 3 options are considered when no correction is applied. And in the third case, we just associate an uncertainty which is defined as 50% of the mean absolute drift as half width of this rectangular distribution. So in this case, we consider the absolute drift of the transfer standard during the all comparison. So no drift associated with a single loop is considered in this third option. We can see an example of pilot values and the loop values. with associated and expanded uncertainty during CCM.3K2 comparison. And we can see the different measurement performed, the different deflections performed in time by pilot measurement, by pilot laboratory, and the loop value evaluated as the mean value, but then, of course, associated with the timing of the participant laboratory, which its uncertainty evaluated according to previous calculations. Regarding parasitic components, this is another very important parameter which has to be considered, and this is due to the interaction between the transducer itself with the standard machines. For force, we usually perform compression mode comparisons because it is very easy to decouple the transducers with the interaction with the machines and interactions with external forces and bending moments. And also the mounting is much easier because we can use a suitable loading pad and centering masks that can minimize the effects of side forces and bending moments. Tension mode comparisons are usually neglected since the influence of adapters and different mechanical parts are not that negligible. In particular, different full standard machines have different sizes of, for example, tension rods, and so more parts in each NMI are needed in order to minimize this effect. So usually this mode is not performed. Regarding torque, both clockwise and counterclockwise directions are performed, and these are possible because the same mounting can be applied. We can see here two examples of shaft connections with flexible couplings, which can work very well in minimizing the influence of external forces and external unknown and parasitic moments. As mentioned, also amplifier has an influence, so we have to assure that the amplifier is stable in time at different pilot and participant laboratories. So usually a calibrator, which is considered stable in time, is circulated together with the transfer transducer. So each laboratory usually use its own amplifier, and this is regularly checked against this calibration. So the amplifier is checked at different voltage ratios, and the corrections are made based on the performance of the amplifier. Another key aspect is that the excitation voltage, the carrier frequency, and also the filter settings shall be the same through the all comparisons in order to minimize the influence of these amplifiers. We can see an example of the behavior of the amplifiers, both at participants and at pilot laboratories, and we can see the different voltage steps here, plus 1 millivolt per volt and minus 1 millivolt per volt, and we can see the time series for these two voltage ratios at the pilots and participants. We can see a similar behavior. So despite different amplifiers were used, we can see a similar behavior. So this was fine in CCM.F-𝐤𝐞𝐤𝐬 comparison, and this is mainly due to the drift of the calibrator itself. So we consider the calibrator stable in time. Instead, we can see that also the calibrator has different behavior and a drift in time. So basically, it might be less stable than the amplifier itself. So it is very important to keep this in mind in order to improve future key comparisons. The other influence factor is the ambient conditions, the environmental conditions. So for this reason, different rules are adopted in different key comparisons. So mainly, it should be allowed to stabilize the force measuring chain and also the torque measuring chain in for at least 1 day before the beginning of the campaign in a temperature and humidity controlled environment like laboratory of different NMIs. And also measurement shall be carried out at fixed temperature and humidity conditions with very tight tolerances. And it is very important, more than the absolute value of temperature and humidity, to keep these tolerances during measurements in time. As a matter of fact, we can correct differences in temperature and humidity conditions when participating laboratory differ from the reference ambient conditions. This is typical for in key comparisons, and for this reason, measurement campaigns are also performed in order to measure temperature and humidity sensitivity, and in order to correct measurements as function of these two environmental factors. As we can see, this is the formula that is usually used to correct the sensitivity as of our transfer standards as function of humidity and temperature. So these RH and ET are the sensitivity coefficients for humidity and temperature. There are different ways to measure these sensitivities, and these measurements are usually time-consuming, but they are fundamental in order to perform this kind of corrections. Also, uncertainty is associated with these sensitivities, basically given by the combination between the uncertainties of the single values from this formula, as well also the contribution, the uncertainty contribution due to the fitting procedure. We can see an example for CCM.F-𝐒𝐤𝐞𝐚𝐤𝐬 comparison, and we can see that deflections are performed by pilot laboratory at different temperature steps in degrees Celsius, from 15 up to 30 degrees, with steps of 5 degrees Celsius, and a straight line fitting procedure is performed, and so the sensitivity coefficient can be evaluated. Here we can see also another example for torque comparison key 1, where a shaft type torque transfer standard was used, and these are the measurements performed by the pilot laboratory, and we can see very strong dependency of deflections as function of relative humidity, as mentioned before, especially for shaft type transducers. And in this way, sensitivities coefficient can be used and to correct comparison measurements. So given these influences and given the solutions for these influences in order to minimize them, which are the main parameters we should take into account to choose the proper transfer standard? So first of all, we should choose stable transfer standards over time with the possibly well-documented history of the transducer. So it is not indicated to use a new transducer because can be more unstable, and we do not have a well-documented history of the transducer itself. We should also choose a transfer standard that has minimum influence due to ambient conditions like temperature, humidity, and so on. And the transfer standard should cover the full range required for the key comparison with adequate resolution in order to minimize the influence of resolution. This should, the transfer standard should also be highly reproducible in order to minimize the influence of of repeatability and reproducibility in order to keep minimum overall uncertainty in the comparisons. And also it should be insensitive to parasitic components. So in summary, we described how key comparisons in force and torque are conducted. We presented which are the typical transfer standards used for this kind of key comparisons, and which are the main parameters affecting the results and the performance of the transfer standards. Also, how to apply relevant measurement procedure to minimize these effects was described, and also the characteristics of the proper transfer standards are listed. Recently, and I want also to mention that a working group on comparisons was established last year within the activities of EURAMET TCM subcommittee force. The idea of this working group is to provide the guide for future regional metrology organization key comparison, guidelines, recommendations, maybe also technical protocols, data collection templates, and so on, and in particular how to link these the results of RMO comparison with BIPM key comparisons. And there are some papers about this, and a proper template and procedure will be provided. Okay, thank you for your attention. And
with that, I would like to thank everyone again and draw this webinar to a conclusion. Thank you.